Yeah, Assalamualaikum, and how are you today? Okay, and hi. Okay, we have discussed on the basic parts of the derivative and its application, and also we have discussed on the implicit derivative, partial derivative, and its application in the previous three learning units. Okay, so for today's learning unit, that is learning unit 12, we will discuss further on the unconstrained optimization, constraints optimization, and the solutions for Lagrange multipliers. Okay, what is unconstrained optimization? Okay, unconstrained optimization is actually optimizing functions without any constraints. Therefore, the strategy in order to optimizing functions without any constraint is the first one is by solving the simultaneous equation to find the stationary point that is at a, b, where we have to differentiate the equation with respect of x, of x, y, and then equate it with 0. Then we have to solve that fy, or the derivative of f with respect of y, that is equal to 0. So based on the tips of the solution, if the second derivative of f with respect of x greater than 0, then the second derivative of f with respect of y also greater than 0, and the second derivative of x, and then f with respect of x multiplied by the second derivative of f with respect of y minus f2xy greater than 0 at the point of AB, then the function has a minimum at AB. But if fxx, or the second derivative of fx, less than 0, then the second derivative of fy, that is fyy, less than 0, and fxx, fyy minus f2xy greater than 0 at the point AB, then the function has a maximum at AB. Okay, then if fxx times fyy minus f2xy less than 0 at AB, then the function has a saddle point at the point AB. For example, find and classify the stationary points of the functions f of xy, given that x cubed minus 3x plus xy squared. Therefore, in this case, we have to do the first derivative with respect of x and the first derivative of this function with respect of y. So when you do the first derivative with respect of x, then we found that we derived in terms of x cubed 3x then xy squared. Therefore, fx is equal to 3x squared minus 3 plus y squared. Okay. Then the first derivative of y will derive on y at this term. However, the other terms will be equal to 0 because of it is known as a constant. Therefore, fy is equal to 2xy. Okay, then the second derivative of fx is equal to 6x, where we derive this 3x squared minus the derivative of 3 plus the derivative of y squared, because of it is the derivative with respect of x, and we only have 6x. Okay, and in addition, the second derivative of fy is equal to 2x, because of the fy we only have 2xy. Therefore, the derivative of fy with respect of y is equal to 2x. Then the last one we have to calculate for the derivative of f with respect of x and y. Therefore, we have to look at the first derivative, that is fx. Then we derive this with respect of y, then therefore we only have 2y. Okay, then according to the rules that been given in the previous slides, in step 1, we have to check for fx of xy equal to 0. Therefore, we have 3x squared minus 3 plus y squared equal to 0. Then we got this as the equation number 1. Then we have fy of xy equal to 0. Therefore, 2xy equal to 0. Then we got this as the equation number 2. Okay, begin with the equation number 2. Then the product of three numbers can be equal to 0 is when one or more of the individual numbers forming the product are 0. Either x is equal to 0 or y is equal to 0. If x is equal to 0, then we substitute x equal to 0 into equation 1. Therefore, 3x squared minus 3 plus y squared is equal to 3 times 0 squared minus 3 plus y squared is equal to 0. And then we found that y squared is equal to 3. Therefore, because of this is an even power, then we have y is equal to square root 3 and y is equal to negative square root 3. Therefore, there are two stationary points here that are located at the 0 and square root 3, and the other one is at 0 and negative square root 3. In the second case, if y is equal to 0, then we substitute y equal to 0 into the equation 1. Therefore, we have 3x squared minus 3 plus y squared equal to 3x squared minus 3 plus 0 squared equal to 0. Therefore, we have 3x squared equal to 3. Then we solve x squared is equal to 1. Therefore, again, because of we have the even power, then the square root of x, or square root of 1, in order to get x is equal to, that will give x equal to 1 and also x equal to negative 1. Therefore, there are another two stationary points, that is at 1, 0 and negative 1, 0. In the step 2, okay, at the point of 0, negative 3, that is based on the calculation in the case 1, then we have to check it by using the formula of the derivative of fxx. Then we substitute that x by 0, therefore 6 times 0 is equal to 0. Okay, then fyy, okay, fyy, it is equal to 2x, therefore we substitute x equal to 0, therefore it's equal to 0. And then fyy equal to 2x, therefore when we substitute this 2 times 0 is equal to 0, then we have fxy equal to 2y, then we multiply 2 by negative square root 3 equal to negative 2 square root 3. Then the last test is we have to substitute into the fxx times fyy minus f2xy. Therefore, it is equal to 0 times 0, then minus in parentheses negative 2 square root 3 square, that is equal to negative 12, that is less than 0. Because of fxx, fyy equal to 0, then fxx, fyy minus f2xy is negative 12, that is less than 0. Then automatically we know that at this point it is having a saddle point. Okay, for the point 0.03 square root 3, again we substitute x equal to 0 and y equal to square root 3 into fxx, therefore we get 0. fyy, 2 times 0 is 0. fxy is 2 times square root 3, therefore 2 square root 3. fxx, fyy minus f2xy equal to 0 times 0 minus 2 square root 3 square equal to negative 12, therefore less than 0. Then this is also a saddle point for 0 and square root 3. Then based on the case 2, at the point of negative 1 and 0, we substitute x equal to negative 1 and y equal to 0 into the fxx, that is 6 times negative 1 equal to negative 6, less than 0. fyy, that is 2x, then we multiply 2 by negative 1 equal to negative 2, less than 0. Then fxy equal to 2y, therefore we have 2 times 0 equal to 0. Then we test fxx, fyy minus f2xy equal to negative 6 because of fxx just now is negative 6 multiplied by fyy that is negative 2, then minus with the f2xy means that the square of the fxy, therefore we have 0 square, then it is equal to 12, that is greater than 0. Then we found that negative 1 and 0 is a maximum point. Then the next is point at the point of 1 and 0 based on the case 2. Therefore, we substitute x equal to 1 and y equal to 0 into the test function. Therefore, we have fxx is equal to 6 times 1, that is greater than 0. Fyy, that is equal to 2 times 1, that is 2 greater than 0. Then fxy equal to 2y, therefore we have 2 times 0 is equal to 0. Then fxx, fyy minus f2xy equal to 6 times 2 minus 0 square equal to 12. Therefore, 1 and 0 is at the minimum point. Okay. Example 2. Okay. A firm has the possibility of charging different prices in its domestic and foreign markets. The corresponding demand equations are given by Q1 equal to 300 minus P1, then Q2 is equal to 400 minus 2 P2. Therefore, the total cost function is given as the TC equal to 5000 plus 100Q, where Q is equal to Q1 plus Q2. Okay, determine the prices that the firm should charge to maximize profit with the price discrimination and calculate the value of this profit. Okay, then in order to solve this, okay, we are given that Q1 is equal to 300 minus P1. Okay, therefore we have to convert this or change it into the function of P with respect of Q. Therefore, we have P1 is equal to 300 minus Q1. Therefore, the total revenue 1 or TR1 is equal to P1 times Q1. Therefore, we have 300 Q1 minus Q1 square. Okay, then where we have here P is TR is equal to 300 minus Q1 times Q1. Okay, then for Q2 we are given that 400 minus 2P. Then we convert this into the function with P with respect of Q. Therefore, we have 2P2 is equal to 400 minus Q2. Therefore, P2 is equal to 200 minus 0.5 Q2. Therefore, TR for the second total revenue or total revenue 2 of the product 2 is equal to 200 minus 0.5 Q 10 times Q. Therefore, we have 200 Q 2 minus 0.5 Q2 square. Then TR is equal to TR1 plus TR2, the combination between the two. Therefore, we have 300 Q1 minus Q1 square. Then plus in parentheses the TR2, that is 200 Q2 minus 0.5 Q2 square. Therefore, TR is equal to 300 Q1 minus Q1 square plus 200 Q2 minus 0.5 Q2 square. Given that total cost is equal to 5000 plus 100Q, where Q is equal to Q1 plus Q2, then the total cost would be equivalent to 5000 plus 100 times Q1 plus Q2, that is equal to 5000 plus 100 Q1 plus 100 Q2. Therefore, in this case, we substitute this Q equal to Q1 plus Q2 into this Q. Therefore, from here, we can calculate, identify for the profit function, that is TR minus TC, that is equal to 300 Q1 minus Q1 square plus 200 Q2 minus 0.5 Q2 square, then minus the total cost. Therefore, we have to put it into the parentheses. Therefore, we have minus 5000 plus 100 Q1 plus 100 Q2. Okay, when we solve it, then we found that the profit function is given by 200 Q1 plus 100 Q2 minus Q12 minus 0.5 Q2 square, then minus 5000. Okay, then at the stationary point, okay, then we have to differentiate the profit function with respect of the Q1. Therefore, we differentiate the 200 q1, then negative q1 square, and the rest is actually equal to the derivatives of the constant uh, value. Therefore, d pi over dq1 is equal to 200 minus 2q1. That is equal to 0. Then we solve for q1. Therefore, we found that q1 is equal to 100 units. Same also for d pi, or the differentiation of the profit with respect of quantity 2. Therefore, we derive in terms of the terms that is having q2. Therefore, we are having here that is equal to 100. That is equal to 100 minus q2 equal to 0. Then we found that q2 is equal to 100 units. Okay. Then we check that the conditions for maximum are satisfied. Therefore, we have to do the second derivative of the profit function with respect of q1. Therefore, the second derivative of this d pi over dq, or the profit function, is equal to negative 2. Therefore, it is less than 0. Then we have to do the second derivative of the profit with respect of q2. Therefore, we have d2 phi over dq2 square is equal to negative 1, and it is also again less than 0. Then we test the fxx, that is given by d2 pi over dq1 square times fyyyy, that is given by d2 pi over dq2 square, then minus fxy square, that is d2 pi over dq1 dq2. Okay, therefore it is equal to negative 2, then multiply by negative 1, then minus 0 square. Okay, minus 0 square equal to 2, that is greater than 0. Therefore, because based on this test, and we found that the condition for maximum are satisfied. Okay, then we substitute q1 equal to 100 and q2 equal to 100 into the demand and profit function. Therefore, p1 equal to 300 minus q1. Therefore, 300 minus 100 is equal to 200. Then p2 is 200 minus 0.5 q2. Then we have 200 minus 0.5 times 100. Then it is equal to 200 minus 50. Then we have 150 ringgit. Then the profit value is equal to 200 times 100 plus 100 times 100 minus 100 square minus 0.5 times 100 square minus 5,000 is equal to 10,000 ringgit. Then we move to the another topic, that is constraints optimization. So constraint optimization is optimizing functions subject to a constraint. Therefore, in general, to optimize a function z equal to f of xy, we call the objective function subject to a constraint p of xy equal to m. P is a known function of two variables and m is a known constant. The problem is to pick the pair numbers xy which maximizes or minimizes f of xy as before. However, we limit the choice of pair to those which satisfy p of xy equal to m. So for example here, find the maximum value of the objective function z equal to 2x squared minus 3xy plus 2y plus 10 subject to the constraint y equal to x. Okay, then given that y equal to x, therefore we can substitute the y with x. Therefore we have here z is equal to 2x squared minus 3x times x, then plus 2 times x, then plus 10. Okay, therefore we have these 2x squared minus 3x squared plus 2x plus 10. Then we simplify into negative x squared plus 2x plus 10. Okay, at the stationary points means that we have to derive this function z with respect of x and equate it with 0. Therefore, we have found that dz over dx is equal to negative 2x plus 2. equal to 0. Therefore, we have 2x is equal to 2, then x is equal to 1. Therefore, because of y is equal to x, then automatically y is equal to x equal to 1. Okay. Then we check d to z over dx squared equal to -2. Therefore, that less than 0, then we found that this is a maximum point. Therefore, the value of z is equal to -x squared plus 2x plus 10. That is equal to -1 squared plus 2 times 1 plus 10. Then we have z is equal to 11. Therefore, the constraint function has a maximum value of 11 at the point of 1, 1. So in the next example of the constraint optimization is a firm's unit capital and labor costs are 1 ringgit and 2 ringgit respectively. If the production function is given by Q equal to 4LK plus L square, find the maximum output at the levels of K and L at which it is achieved when the total input costs are fixed at 105. Then verify that the ratio of marginal product to price is the same for both inputs at the optimum. Therefore, based on this, we can create the objective functions that is given has the Q equal to 4LK plus L squared. But for the constraint, because of in the question, it mentions that okay, a firm's unit capital and labor costs are 1 and 2 respectively, and then okay, the levels of K and L is achieved when the total inputs costs are fixed at 105 ringgit. So based on this information, then we create the constraint function that is given as the K. Why it is K? Because of we have 1 ringgit cost for the capital, okay, and then we have 2 ringgit cost for the labor. Then we set it up as the K plus 2L equal to 10, equal to 105. Sorry, 105. Okay, then the first step, rearranging the constraint to express K in terms of L. Therefore, it gives K plus 2L is equal to 105. Then we solve for K. K is equal to 105 minus 2L. Okay. Then we substitute this value of K equal to 105 minus 2L into the Q equal to 4LK plus L squared, the first function here. Therefore, we found that Q is equal to 4L times 105 minus 2L plus L squared. Therefore, we have Q equal to 420L minus 8L squared plus L squared. Then we have 420L minus 7L squared. Therefore, at the step 3, at the stationary point, dq over dl is equal to 0. Then we derive Q with respect of L. Therefore, dq over dl is equal to 420 minus 14L. Then L is equal to 30 Okay. Then we differentiating a second time. Therefore, we have d2q over dl square. That is equal to -14. And it is less than 0. Then here we prove that this L is actually a maximum point. Okay, substituting L equal to 30 into the objective function, therefore we have Q equal to 420 times 30 minus 7 times 30 squared. Therefore we have 12,600 minus 6,300, then we have 6,300 units. Then we substitute L equal to 30 into the constraint. Therefore, K is equal to 105 minus 2L equal to 105 minus 2 times 30. Then we have 105 minus 60 equal to 45 units. Then, based on this, we found that the firm should therefore use 30 units of labor and 45 units of capital to produce a maximum output of 6,300 units. Okay, from Q equal to 4LK plus L squared, we can create or calculate the MPL or marginal product of labor, that is 4K plus 2L by differentiating Q with respect of L. Then we can also calculate for MPK, or marginal product of capital, that is equal to 4L when we differentiate Q with respect of K. Therefore, at the optimum, the value of MPL is equal to 4 times 45 plus 2 times 30, that is 240, and MPK is 4 times 30, that is equal to 120. Therefore, the ratios of marginal product are then given by MPL over PL, that is 240 divided by 2, that is 120. And then MPK over PK, that is 120 divided by 1 equal to 120. Therefore, this shows that both of the calculations are given the same value. Okay, then now we move to the next part, that is on the solving sets related to the Lagrange multiplier. So we can obtain maxima and minima for a function z equal to f of x subject to the constraint g of x y equal to 0 by using the method of Lagrange multipliers. Lagrange multipliers can be used with functions of 2 or more variables when the constraints are given by an equation. Therefore, in order to find the critical values of a function f of xy subject to constraint g of xy equal to 0, we will use the new variables lambda to form the objective function. So instead of having x and y as a function of f, okay, then here we have the lambda. Therefore, we have f of xy lambda is equal to the combinations of or objective function that is given by f of xy plus with the constraint function that is lambda g of xy. Therefore, here it can be shown that the critical values of f of xy lambda will satisfy the constraint of g of xy and will also be a critical points of f of xy. Okay, then we only need to find for the critical points of f of x, y, lambda to find the required critical points. Okay, then to find the critical points of f of x, y, lambda, we must find the points that make all the partial derivatives equal to 0. That is, the points must satisfy that the derivative of x with respect of x equal to 0, the derivative of this f with respect of y equal to 0, and the derivative of f with respect of lambda is equal to 0. Because of f of xy lambda is equal to the objective function that is f of xy plus lambda g of xy. L here is actually representing the lambda. Okay, sometimes you put L, sometimes you put that this this symbol. Okay. Then this equation can be solved or written as the df over dx plus lambda dg over dx equal to 0. Then we differentiate the objective function with respect of x here. Then plus with the lambda times the derivative of g with respect of x. Okay, then we equal to 0. The second function, we found that the derivative of function f with respect of y on the objective function plus with the lambda times the derivative of g with respect of y, then equal to 0. And the last one is g of xy must be equal to 0. Then finding the value of xy that satisfy these three equations simultaneously gives the critical values. Okay, for example, here find the maximum value of z equal to x squared y subject to x plus y equal to 9, where x is greater than or equal to 0, y is greater than or equal to 0. Okay, therefore for the solution, the function to be maximized is f of xy equal to x squared y. Then the constraint function is given by g of xy equal to 0. Therefore, we have x plus y minus 9 has the constraint function. The objective function is given as the f of x, y, lambda, that is equal to the objective function plus with the constraint function. Therefore, we can set it as the f of xy plus lambda g of xy. and then or we can expand it into f of x y lambda is equal to x square y, that is given by this function z, then plus lambda times x plus y minus 9, that is given by this function. Okay, thus from that function we derive the function of f with respect of x. Therefore we have 2xy, okay, 2xy plus lambda, okay, plus lambda times 1, that is equal to 0. Therefore we have 2xy plus lambda equal to 0. This is equation number 1. Okay, then df over dy, therefore we have x square plus lambda times 1 equal to 0. Therefore we have x square plus lambda equal to 0. This is equation number 2. Then we have df with respect of d lambda equal to 0 plus 1. Okay, we differentiate the lambda, therefore lambda is equal to 1 times x plus y minus 10 equal to 0. Therefore we have the third equation that is given by x plus y plus minus 9 equal to 0. Okay, then from here, solving the first two equations for lambda and substituting will gives lambda, based on this, lambda is equal to negative 2xy. This is from equation 1. Okay, then lambda is equal to negative x2, that is from equation 2. And then we have here 2xy is equal to x squared. Okay, and then therefore 2xy minus x squared is equal to 0, and then x times 2x minus y is equal to 0. Okay, okay, because x equal to 0 or x equal to 2y could not make z equal to x square y a maximum. Therefore, we substitute x equal to 2y into x plus y minus 9 equal to 0. Therefore, we have 2y plus y equal to 9. Therefore, y is equal to 3. Then x can be calculated as the x plus 3 minus 9 equal to 0. Therefore, x is equal to 6. Therefore, thus the function of z is maximized at z is equal to, in parentheses, 6 square times 3 and then equal to 110 and 108. Therefore, this function is maximized at 108 when x is equal to 6, y is equal to 3, if the constraint is x plus y equal to 9. Then the testing values near x equal to 6, y equal to 3, and satisfying the constraint shows that the function is maximized there. Okay, we have another examples here. Suppose that the Cobb-Douglas production function for a certain manufacturer gives the number of units of production z according to z equal to f of x y equal to 100x power 4 over 5 y power 1 over 5, where x is the number of units of labor and y is the number of units of capital. Suppose further that labor costs $160 per unit, capital cost is 200 unit per unit, $200 per unit, and the total cost for capital and labor is limited to 100,000, so that the production is constrained by 160x plus 200y equal to 100,000. Then find the number of units of labor and the number of units of capital that maximize the production. Therefore, the objective function for this problem set can be set up as the f of x y lambda, that is equal to 100x power 4 over 5 y power 1 over 5, that is given by the objective function in the questions, plus with the constraint function that is given by lambda times 160x plus 200y minus 100,000. Then we differentiate this objective functions, okay, with respect of x, therefore we have 4 over 5 times 100 x power negative 1 over 5 because of power 4 over 5 minus 1, means that 4 over 5 minus 1 over 5 over 5, then y power 1 over 5, and the derivative of the constraint here with respect of x will give us 160 lambda. Okay, and then because of we derive in terms of this, the rest are constant, sorry. Then the derivative of this function f with respect of y will give us 1 over 5 times 100, that is 20, x power 4 over 5 is remain the same, but the difference here is y power 1 over 5 minus 5 over 5 is equal to y power negative 4 over 5, then plus the differentiations of the lambda, this function with respect of y in the constraint function will give us 200 lambda. Then the derivative of this function with respect of lambda will give us only the value in this parenthesis, that is 160x plus 200y minus 100,000. Then setting these partial derivatives equal to 0, then we solving gives lambda is equal to negative 80x power negative 1 over 5 y power 1 over 5 divided by 160. This is based on the transforming of the equations of the df over dx. Okay, then lambda also equal to, okay, negative 20, where we're transforming df over dy here, therefore we have negative 20x power 4 over 5 y power negative 4 over 5 divided by 200, or y power 1 over 5 divided by 2x power 1 over 5 is equal to x power 4 over 5, and then divided by 10y power 4 over 5. So this means that 5y is equal to x. Therefore, using this in df over d lambda equal to 0, then we found that we found that 160 times 5y plus 200y minus 100,000 is equal to 0. Then we can solve for y. Therefore, we have y equal to 100. When y equal to 100, then we substitute into the equations, where we have 160x plus 200y minus 100,000. Therefore, we change it into 160x plus 200 times 5 minus 100,000. Okay, then we found that x is equal to 5y, that is equal to 500. Okay, then this is actually the graph that shows the production is maximized at z equal to 100 times 500 power 4 over 5 times 100 power 1 over 5, that is giving us the approximately equal to 36,239, when the capital X is equal to 500 and the capital Y is equal to 100, that has been shown in the figure 14.14. Therefore, in a problem of this type, economists call the value of the negative lambda here has a marginal propensity of money. So in this case, the negative lambda is equal to the y power 1 over 5 divided by 2x power 1 over 5, that is equal to 100 power 0.2, then divided by 2 times 500 power 0.2, that is approximately equal to 0.362. Therefore, what does it mean by this value is each additional dollar spent on the production results in approximately 0.362 additional unit produced. Then the figure just now, that is 14.14, shows that the graph of the constraint together with some production function curves that correspond to the different production levels. Okay, we already end up with all those topics that related to derivative. I hope that you can acquire all the skills starting from the learning unit 9 until learning unit 12, and then you have to understand how to do the basic derivative or explicit derivative. Then after that, you have to know how to use and apply the implicit derivative, and also as well as partial derivative.